In the previous video, we had introduced the basics of convolutional neural networks. We had also introduced all the different types of operations and the layers that constitute a typical convolutional neural network. In this video, we will discuss the basics of training a convolutional neural network. We will discuss the basics of the backpropagation algorithm as it applies to a convolutional neural network, as well as some visualization applications of backpropagation. The backpropagation in a convolutional neural network is conceptually not very different from that in a conventional neural network. In a conventional neural network, we always maintain the gradient of the loss function with respect to the various hidden variables. So in each layer, you compute the partial derivative of the loss function with respect to each hidden variable, and then you backpropagate this matrix of hidden variables in the backward direction. In a convolutional neural network, you have three-dimensional layers with height, width, and depth. Correspondingly, you backpropagate the partial derivative of the loss function with respect to the elements in these three-dimensional layers in the backward direction. And once you have these partial derivatives, you convert them into derivatives with respect to the weights with the use of one further application of the chain rule. So in the case of the convolutional neural network, the main difference is in terms of how the gradients are propagated backwards in the case of convolutions. Note that the case of ReLU is very similar to a conventional neural network. As in a conventional neural network, it's a one-to-one operation. Each element, you take the max of that element and zero. Similarly, in a convolutional neural network, for a three-dimensional layer, you create a corresponding three-dimensional layer in which all the negative elements are set to zero. While backpropagating, you use the same rule as you would use in the case of a conventional neural network, is that you pass the gradient to a previous layer only if the original input value was positive. The max pooling operation is also somewhat similar in that it selectively passes the gradient flow. However, in the case of a max pooling, you pass the gradient flow through the largest cell in the input volume. All the other cells, the gradients are set to zero. So the ReLU and the max pooling, they are very similar operations, and even in a conventional neural network, if you ever use the max operation, this is a similar kind of operation if you use the max operation in a conventional neural network. So these are fairly obvious. The main complexity in the case of the convolutional neural network arises in terms of how you perform backpropagation through convolutions. Because convolutions, in essence, are matrix multiplications, except that these matrices are sparse and also that the weights are shared across the whole volume. So this requires some changes to the backpropagation algorithm. However, as we'll see, the backpropagation operations are still intuitively quite similar to conventional neural networks. Now, when you look at a traditional neural network and when you perform a forward propagation in a conventional neural network, when you look at the linear operation, just the operation that uses the weights, that's essentially a matrix multiplication. Similarly, when you backpropagate the partial derivative with respect to the layer variables in a conventional neural network, all you have to do is to multiply this backpropagated matrix with the transpose of the corresponding matrix to propagate it backwards. We discussed this in our previous lecture on backpropagation. Now, in the case of convolutions, we have a very similar type of interpretation. You can represent these backpropagation through convolutions as transposed convolution with an inverted filter. So instead of transposing the matrix, you are inverting the filter. Now, there are two ways in which one can write an algorithm for backpropagation with convolutions. One is a simple element-wise approach. That is also discussed in the book. There's a pseudocode given in the book. So essentially what you can do is that you can look at which cell of the input corresponds to which cell of the output. And you can use this fact in order to appropriately accumulate the gradients. The second approach and the more more easy to understand approach is by looking at them from the point of view of filter operations. So when you have the backpropagated set of gradients, so imagine you have a layer in which you have backpropagated all the gradients in that layer. Let's say layer I plus 1. So for each element in that layer, you have the partial derivative of the loss function with respect to each element in that layer. Now you can show that backpropagating this gradient to the previous layer can be done by multiplying with an inverted filter. And once you have the derivative with respect to the layer, you can convert the layer-wise derivative to a weight-wise derivative. This is done in conventional neural networks also by essentially multiplying with the hidden variable connecting the weight as well as the backpropagated gradient. So, and once you have these derivative with respect to the weights, note that weights are shared across the layer. Then you have to add up the this derivative with respect to each copy of the shared weight over all the weights. So let's look at one of these two ways of performing convolution with an inverted filter. For simplicity, let's just consider a very simple case where you have a layer with a depth of 1. That means that there's only one channel. You use only one filter. So you don't have multiple filters, you just have one filter. So again, you'll have only one output channel. So you will have one input channel and one output channel. And let's say that your filter during convolution looks like the filter on the left. You can see the elements are A, B, C, D, E, F, G, H, I. The question is, at the time of backpropagation, once we have the backpropagated, the loss derivative with respect to all the elements in the output layer, how do you perform the backpropagation as a convolution? You can show that multiplying, if you treat this output channel, the loss derivative as a layer of values, the partial derivatives in the output channel, then multiplying those gradients, that layer of gradients with respect to this inverted filter, the one shown on the right, will give you the backpropagated gradients with respect to the previous layer. And a justification for this is given in the book. Now this only shows you the result for a very simple case where you have one input and one output. What do you do in the case where you may not have, where your input channel may have a depth of more than 1 and your output channel has a depth of more than 1. So just for argument's sake, let's say that we perform, we have 20 filters for 3 input channels. So let's just talk about the input layer to the first hidden layer and how we backpropagate the gradients all the way back to the input layer. Now normally you don't perform backpropagation to input layers, normally you stop at the first hidden layer, but the argument is true for any pair of layers, and it's easier to explain with respect to the input layer because I can give names to the channels, red, green and blue. So let's say that you have 20 filters for your 3 input channels, R, G, B. So it's going to create an output layer with 20 channels. So your output layer will have depth 20. So the question is, once you backpropagate the gradients with respect to that output layer, so you will have that whole 3-dimensional volume of depth 20 with all the partial derivatives with respect to each cell in that output layer. What 3-dimensional filter should I multiply it with in order to get our gradients with respect to our input layer with just 3 channels? Now note that since we have 20 filters with 3 input channels, each filter has 3 channels, so you have 60 spatial slices. So what we'll do is that we will invert these 60 spatial slices in the same way I have shown in the diagram in this slide. And then you will again group them into 3 sets of filters of depth 20. The way you will group them is when you had those 20 filters which you used to transform to the output layer, you always had a red channel filter. One of those 3 was always a red channel filter. So you pull out all the filters, all the 20 filters of the red channels, you group them together to create one filter of width 20. Similarly, you pull out all the inverted filters for the green channels and you create one filter of depth, and similarly you pull out all the filters for the blue channel and you create one filter of width 20. So now you have these inverted filters and you have grouped them into 3 filters, each of which has depth 20. And now you will multiply our output layer which has depth 20 with each of these three filters to get our gradients with respect to the input layer. So this approach is used in every layer. Here I only discussed from input to first hidden layer, which is actually very rarely used. Usually you use it between pairs of hidden layers, but this general argument is true across all pairs of layers. And a brief discussion of this and a justification of why you invert the filter is also given in the book. Now, another way of looking at convolution is that you can present convolution operation as a matrix multiplication. Presenting a convolution operation as a matrix multiplication is very useful because it's very useful both during forward propagation as well as a backward propagation. Because for forward propagation, all you have to do is to just multiply a reshaped input layer with with the matrix in order to get the elements of the next layer, and the back propagation can be presented as a transpose matrix multiplication. This type of approach actually shows even more clearly why convolution is very similar to a matrix multiplication. So I'll just give an example here, and a more detailed discussion is given in the book. So let's say that you have this input, this 3x3 input, which has just one channel. Just for simplicity, let's just look at input with one channel, and correspondingly, of course, you'll have a filter with one channel. So you have a 2x2 filter. Now, what we are going to do, we are going to convert this input into a 9-dimensional vector. So, and we are going to convert this filter. Now, this filter can be aligned at 4 possible places on this 3x3 input, because if you use a side of 1 and let's say you're not using padding, there are 4 possible places you can align this filter with the input. So you're going to create a matrix which has 4 rows correspondingly, and it has 9 columns. Why 9? Because the input has 9 elements. So you are going to create a 4x9 sparse matrix C. Now, how is each row of this sparse matrix going to be defined? Each row of this sparse matrix C is going to be defined by one placement of the filter at a particular place in the input layer. So let's say that you align the filter with the top left of your input. So the first, and let's look at the top row of the matrix C, which is A, B, 0, C, D, then 4 zeros. So you can see that when you flattened your input to a 9-dimensional vector, the first row, when you align the filter with it, A and B will be the first 2 elements, and then because the filter is not aligned with the third element, you'll just set it to 0. Then in the flattened row, again the C and D come, so you can see A, B, 0, C, D. That's the first row of the matrix C, and then because the filter is not aligned with the last row of the input, the last 3 elements are all zeros. So you can see this is how you get the first row. The second row corresponds to the second alignment of the filter. The second alignment of the filter is the alignment of the filter with the upper right of the input. So here you can see the first element of the second row of C is 0 because it's not aligned. The filter is no longer aligned in the top left corner. However, the second elements are A, B, and then we move on to the second row of the input, which will be 0 because the filter is not aligned there. And then you will get your C, D, and then again because the filter is not aligned with the last row of the input, you'll have a bunch of zeros. You'll have 3 zeros. And this is how you'll also create the last row. So you will get this 4x9 matrix. And then what you'll do, this 1-dimensional vector that you got, you're going to multiply this C. We are going to multiply it with this 1-dimensional vector F that you got, that you flattened your input. And that's how you're going to get an output which is 4-dimensional. And the reason it's 4-dimensional is because your output will have 4 elements corresponding to the 4 alignments of filter, and you'll reshape to your spatial output. And the way you'll reshape the spatial output, the ordering will follow the same ordering that you used to define your rows of the rows of the matrix C. So the ordering of the rows of the matrix C, that's how you'll reshape according to that, and that's how you will get your output. And I'll leave you to verify that if you multiply this filter with this input, you will get the output shown at the bottom. Now, this of course is a very simple case. If we had multiple channels, then you won't be just flattening to a vector. This f is a vector here. You'll be flattening to a matrix. But it will still, you can show that you can do this. You can decompose this into matrix operations. Now, the neat part about this type of approach is that you can show that during backpropagation, when you compute the gradients, you can again maintain them as vectors and matrices, and you can multiply by the transpose of this matrix C. So this type of approach shows more clearly how convolution can also be presented as a matrix multiplication. Now, backpropagation has a number of useful applications. One very useful application of backpropagation is gradient-based visualization. In gradient-based visualization, one can backpropagate all the way back to the input layer. And by backpropagating all the way back to the input layer, it tells us something about for the output, which pixels in the input layer are responding to the output. So imagine a case where your output O is the probability of a class label like dog. And let's say you have an image containing a dog, and this output O, this probability lights on. It is a very high probability that it's a dog. So what you want to find out is that how much is each pixel, each xi, let's say xi is one of the pixels in your input image, and you want to find out how much does each pixel, how sensitive is my output to each pixel in the input image. So what you can do is that you can use backpropagation to backpropagate it all the way to the input layer. Now, for training a neural network, you never really need to backpropagate all the way to the input layer. You usually stop at the first input layer, but let's say that we backpropagate it all the way to the input. And then you will have a three-dimensional volume of these partial derivatives. So you will have the partial derivative with respect to each pixel. So let's say your input was a 24 cross 24 cross 3 image. You will have these partial derivatives, the partial derivative of the output dog with respect to each of these 24 cross 24 cross 3 elements, each of these xi's. And then what you can do is that over the three channels you have red, green, blue, you can calculate the absolute magnitude of del O by del xi, and you can set it to a single channel. So you can create a single grayscale image using this type of approach. So you can create one channel by taking the maxima over the three colors. So that way you'll get a 24 cross 24 image, and let's look at what these 24 cross 24 images look like when you use this type of approach. Now, this figure I have shown from Simonian's paper. So here you can see there are two images where the first image on the left, it shows an animal, and when we backpropagate the output with respect to each pixel, and I've shown the visualization in the bottom, you can see that the derivative with respect to the portion of the image corresponding to the animal lights up. And this makes a lot of sense because the output label is most sensitive to these pixels. Because if you change these pixels, the output label is most likely to change. And a similar type of effect is shown in the slide on the right. Now, one can use this type of vanilla backpropagation, but you can often get cleaner visualization by making some minor changes to this type of backpropagation operation. And there are two variations of backpropagation. One is called deconnet and the other is called guided backpropagation. Now, these changed forms of backpropagation are identical to traditional backpropagation. The only difference is in how the ReLUs are treated. Now, the normal backpropagation, as we discussed in the first slide, it passes on the gradient through the ReLU only when the input is positive. Deconnet, it passes on a gradient through the ReLU when the backpropagated gradient, when the actual value of that derivative is positive, otherwise you set it to 0. Now, there's another variation which is guided backpropagation that is also useful for visualization. That is a combination of the traditional gradient-based visualization and deconnet. So in deconnet varies from traditional backpropagation in terms of how you treat the ReLU, in terms of what is the rule for setting an entry to 0. So the two methods, they have different rules for setting an entry to 0. Traditional backpropagation, it sets an entry to 0 when the input is positive. DConnet sets an entry to 0 during backpropagation if the backpropagation gradient is positive, when the output gradient is positive. So in this case, what in guided backpropagation, what you do, you set an entry to if either of these two rules sets an entry to 0. So more entries will be 0 in the case of guided backpropagation. So let me give you an example of DConnet and guided backpropagation. So let's say that on the top I have shown the forward pass. When you apply a ReLU operation. So you can see that when you apply the ReLU operation, it sets some of the entries to 0. And that's a traditional ReLU. It's only setting those entries to 0 which are negative. So you can see there's -1, -2, and -2. There are 3 entries which are 0 in the top left. And those 3 entries, there are 3 entries which are negative, and those 3 entries are set to 0. Now, when you backpropagate, how does this affect during backpropagation? So I've shown all the 3 cases. How do you backpropagate from gradient from layer I plus 1 to layer I? Traditional backpropagation is easy to say. This is how any conventional neural network would do it. You can see you set those same entries to 0 for which the input was negative during the backpropagation. However, in DConnet, what you're really doing is that you're applying a ReLU on the gradients of the layer I plus 1. So when you apply a ReLU, you can see that different entries are being set to 0. 4 entries are being set to 0. That's the top left entry, which is -3. That is set to 0. The top right entry, which is -1, that is set to 0. The middle left entry, which is -1, that is set to 0. And the bottom right entry, which is -4, that is set to 0. Now, in guided backpropagation, this is a combination of traditional backpropagation and DConnet. So, if any of the entries were set to 0 in either of these two cases, they are set to 0 in guided backpropagation. So, the main advantage of guided backpropagation is that it tends to give cleaner visualizations as compared to using just traditional backpropagation. Now, in the previous example, I showed some cases of visualizations of the output feature. So if your output was, for example, a dog, I want to visualize which part of the image is the dog label most sensitive to. So that's what these visualizations tell you. But you can also do it for the hidden features. You can also look at, rather than looking at the feature in the output layer, you can look at the feature in the hidden layer and see, do certain portions of the image tend to activate these features? Do certain portions of the image light up when I compute these gradients with respect to these features? Now, I have shown these corresponding visualizations from image. This is from Springenberg's et al.'s paper. So you can see in each case, for each row, a particular hidden feature has been picked, and we have seen what the corresponding image crops are in your original image, as well as what that light up, the way that we compute backpropagation, and then we visualize what that shows. So that's on the left. That shown on the left under guided backpropagation, and the image crops are shown on the right. So as you can see, each time this type of gradients, they light up for particular types of images. So you can see what the features are learning. They're looking for particular shapes in layers. So in some cases, they're looking for example, faces of dogs, or for faces of people, or for particular parts of flowers. So you can see very clearly that the features in the hidden layer, it kind of gives you an intuitive understanding that the gradients of features with respect to the input pixels, they are sensitive to particular parts of the image, and they light up when the image contains particular types of features. So that is what is meant by this hierarchical feature engineering that is performed in various layers. And in fact, in the book, I also have some visualizations which show the images in various layers. So you can actually see that in the earlier layer, it tends to light up for more primitive type of features, and the later layers, these gradients, they tend to light up for more complex types of features. Now, there's another type of trick that you can apply. You can also learn the for a particular type of output. So for example, let's say O is the unnormalized score of banana. So you might want to learn an input image X that maximizes the output O while applying regularization to X. Now note that we do have to apply regularization. That's very important here. Otherwise, you will not get meaningful visualizations. So here, what you are trying to do, you are trying to maximize the score of O. So what you are trying to do, you already have a trained neural network. So let's say you trained a neural network using a large data set. But now what you do, you hold its weights fixed. Normally we train the weights of a neural network. Here our training is somewhat different. We are trying to find the input image that is most likely to light up a particular output, like for example a banana or a goose. What kind of image would be most likely to maximize the score of banana? So again, you can perform backpropagation to compute the gradient of this output with respect to each pixel, and then you can update X. You can use those gradients to update X while keeping the weights fixed. So this is a very unusual way of using backpropagation. You aren't training the weights. You're holding the weights fixed, but you are updating the inputs. You're trying to find out which image is most likely to light up this particular type of output. And again, we get some very neat visualizations here. So for example, you can see that for an output corresponding to cup, it gives an image which has many cups inside it. It's not one neat cup, but it's got many types of cups inside. Similarly for Dalmatians, you get an output with many Dalmatians inside. And similarly for goose, you can see that there are multiple gooses inside the image. Now, these ideas of gradient-based visualization and gradient-based backpropagation, they can be generalized to autoencoders. And these convolutional autoencoders, they also use this kind of deconvolutional operation, which is very similar to backpropagation. And one can also combine pre-training with backpropagation. And the details of these types of convolutional autoencoders are given in the book.